Okay, let's dive into this. Welcome to today's Explainer, where we're going to take a journey into literally one of the most extreme, mind-bending environments in the entire universe. Now, as undergraduate science students, you've probably encountered some pretty complex equations describing gravity and spacetime. But today, we're going to make those concepts completely visceral. We're breaking down the actual mechanics of what happens when matter meets the ultimate cosmic abyss. So grab your mental spacesuits because we're heading straight for a black hole. So, what actually happens when you get too close? It's a question that has absolutely captivated astrophysicists and science fiction writers for decades. You always hear about the event horizon, right? That ominous point of no return. And the singularity at the center, where our current laws of physics just completely break down. But the journey from the edge to the center is where the real physical drama happens. Today, we're going to strip away the complex mathematics of general relativity and use concepts you already know to uncover the fascinating and, frankly, completely violent reality of this journey. First off, we have to clear something up. Pop culture loves to treat black holes like giant, insatiable cosmic vacuum cleaners, just aggressively sucking up everything in the galaxy. But the Newtonian reality, it's actually far less malicious. From a distance, a black hole's gravitational pull is no different than a star of the exact same mass. I mean, if we were to magically replace our sun right now with a black hole of equal mass, Earth wouldn't suddenly get sucked in. No way. We'd just continue orbiting exactly as we do right now. Though, okay, without the sun's light and heat, we would definitely freeze to death rather quickly. But the point is, the true danger only begins when you get incredibly, uncomfortably close. To safely explore this danger zone, we're going to deploy a theoretical probe. Let's just call it our little robot. And here's the secret to our explainer today. Rather than bogging ourselves down in the dense tensor calculus of Einstein's general relativity, we're going to track our little robot's demise using accessible, classical Newtonian mechanics. As researchers have pointed out, we can understand the core physics of this destruction just by looking at classical tidal forces. So let's drop our little robot in and watch what happens as it falls toward the abyss. As our robot approaches the black hole, it encounters a phenomenon with a wonderfully ridiculous name for a totally terrifying process: spaghettification. This is the vertical stretching and horizontal compression of an object into a really long, thin shape caused by extreme tidal forces. Because a black hole contains so much mass packed into such a tiny, dense area, the gravitational field around it changes incredibly rapidly over very short distances. This creates a severe gravitational gradient. The legendary theoretical physicist Stephen Hawking famously described this in his book, A Brief History of Time. He imagined a fictional astronaut falling feet first toward a black hole and noted that they would be stretched like spaghetti. It's a highly memorable, visceral image, isn't it? It paints a picture of gravity not just as a force that pulls you down, but as a force that pulls different parts of you at violently different rates. Now, what's really interesting about this slide is how you can clearly see those tidal forces at play. If our little robot is falling feet first, the distance between its feet and the black hole is slightly less than the distance between its head and the black hole. And because gravity follows an inverse square law, that tiny, tiny difference in distance means the gravitational pull on the robot's feet is significantly stronger than the pull on its head. Think of it like a rubber band. If you pull the bottom of a rubber band much faster than the top, the whole thing stretches out. At the same time, the angle of gravity pulls the sides of the robot inward toward the center of the black hole, squeezing it horizontally. Let's break down the exact sequence of our little robot's destruction. Step 1. The uneven gravitational pull begins, creating that extreme gradient. Step 2. The vertical stretching kicks in. Our robot's metallic hull elongates just like that rubber band being pulled to its absolute limit. Step 3. Horizontal compression squeezes the robot's sides inward. And finally, Step 4. Materials have physical limits. The tensile strength of our little robot's titanium shell is literally no match for the fundamental forces of the universe. The rubber band doesn't just stretch forever, it snaps. The robot is structurally shredded into pieces, then into individual atoms, and eventually into a stream of hot plasma. It's at this point, as a long, shredded stream of atoms, that our probe's remains cross the event horizon. This is the ultimate milestone, the boundary of no return. The gravitational pull here is so intense that the escape velocity actually exceeds the speed of light. Since nothing in the universe can travel faster than light, nothing, no signal, no radiation, no shattered piece of our little robot can ever escape back to the outside universe. To an outside observer, the robot's image would actually appear to slow down and freeze, turning red as the light stretches. But for the robot itself, it's plummeting inward at a horrifying pace. And this brilliantly illustrates just how fast the end comes. According to simulations run by NASA astrophysicists on supercomputers, if our probe were falling into a supermassive black hole, like the one right at the center of our Milky Way, weighing millions of times the mass of our sun, once it crosses that event horizon, complete destruction and arrival at the singularity is just 12.8 seconds away. Think about that. Just under 13 seconds to cross roughly 79,000 miles of violently warped space-time. But the physics of the journey aren't over just because the robot is in pieces. We have to shift our focus now. We've used classical Newtonian tidal forces to understand the macroscopic shredding, the snapping of the metal. But as this stream of matter hurtles toward the singularity in its final few seconds, the rules of the game completely change. We move from mechanical destruction into a realm dominated by bizarre physics, extreme thermodynamics, and quantum effects. Researchers analyzing what they playfully call hot spaghetti have looked closely at the viscous gravitational collapse of this material. As the tidal forces continue to aggressively stretch and squeeze the remains of our probe, immense internal friction is generated. This causes extreme viscous heating. The material is crushed into a cork glue in plasma. In fact, the gravitational shear forces change so rapidly that the very laws of fluid dynamics, hydrodynamics, break down completely. The plasma literally can't even respond fast enough to the changing gravity. It just becomes microscopic chaos. To really grasp the scale of that friction, consider the numbers. In specific theoretical models of matter collapsing into a black hole, the viscous heating can cause temperatures to spike to 2.8 times 10 to the 8th power giga-electron volts before the hydrodynamic models totally fail. That is an absolutely mind-blowing temperature, far beyond anything a normal star produces. Our little robot isn't just physically broken. It is violently, thermodynamically boiled down into a screaming hot stream of fundamental subatomic particles just moments before hitting the singularity. Now, you might think those particles and their energy are trapped in the black hole forever, right? Well, quantum mechanics gives us a really fascinating twist ending. As Stephen Hawking discovered, empty space isn't empty. It's boiling with pairs of virtual particles just popping into existence. When this happens right on the edge of the event horizon, sometimes one particle falls in and the other escapes. To balance the cosmic energy ledger, the black hole must lose a tiny bit of mass. Over trillions of years, the black hole will slowly evaporate through this Hawking radiation, effectively radiating the energy of our little robot back out into the dying universe. Which brings us to our final, incredibly provocative thought. Quantum mechanics insists that information can never be truly destroyed. Some physicists theorize that the information of our little robot isn't lost inside the singularity, but is actually encoded or painted onto the 2D surface of the event horizon, almost like a cosmic hologram, before slowly leaking back out through Hawking radiation. So as you continue your physics studies, I'm going to leave you with this. If the data that made up our probe is stored on the black hole's surface and eventually radiated back into the cosmos, was our little robot ever truly destroyed at all? Think about that, and keep exploring the amazing mysteries of our universe.